banking application for implementing the fingerprint authentication. And after that, I'm gonna talk about current issues of this way, and finally I provide a better solution and more secure solution for that. Before I start our main topic, I need to explain how we measure security of a mobile application. Basically, when we test the security of a mobile application, we suppose an attacker has full access to the device. That means the attacker has physical access, the device is rooted, all security mechanisms of the operation system already has been disabled, and there is no lock screen, so attacker can easily plug the device to his or her own computer and has the root access to the device. So in that case, still the application must be able to protect its data and keeps them confidential. Okay, let's first take a look at the whole problem. In mobile banking application, usually for authenticating the user, one-time password or one-time padding is used because of its security. In order to generate an OTP, the server-side application and the client-side, or the mobile application, need to exchange a secret key, which will be used for generating the OTP. The security issues about this key is that the key must be stored on the device after activating the application for the future uses and generating the OTP. The secret key must be encrypted on the device, because if you store the secret key as a plain text on the device, anyone or an attacker can access that and reproduce the OTP and authenticate to the system and hijack a session or maybe hijack bank accounts. And that secret key must be just decrypted by the authorized user, by the owner of the account activated on the phone. Everything is all right so far, but the problem occurs when you want to add new way of authentication to your mobile application. It could be fingerprint authentication, it could be face recognition, voice recognition, or any other type of biometric or traditional way of authentication. In that case, the same secret key must be used for any type of authentication. Why? Because different secret key generates different OTP, and the server-side application cannot recognize you and cannot authenticate you. So your authentication will be failed. OK, let's first see how the traditional manner, which is the PIN code authentication, works. Definitely all of you has experienced that. It works with a PIN code. It can be usually 4 digits number, and some applications are more flexible and allow you to obtain a PIN code between, for example, 4 to 8 digits. First, when a user wants to start using a mobile banking application, after installing the application, the user receives some activation information from the bank. It could be a QR code or some other codes in order to activate for the first time the application. The user enters the information. The server-side application, based on the validity of the received activation information, respond to that. In case of the valid information, usually the server-side application returns a secret key, which will be used for generating the OTP. Once the mobile application receives the secret key, manage to encrypt that with a PIN code and stores on the device. Usually in Android application, the mobile application uses the shared preference in order to easily access data in the future. Next step, when the user wants to use the application, the secret key must be decrypted. In 2 times, the secret key is needed. when the user wants to log into the system and when the user wants to sign a transaction. An OTP should be generated for those purposes. First, the user enters the PIN code, and the mobile application tries to decrypt the encrypted secret key on the device with that PIN code. In case of successful decryption, the mobile app can retrieve the plain text of the secret key and manage to generate OTP, send the generated OTP tag along with other information, might be username, might be IBAN number, account number, or anything else, to the server-side application. Please keep in mind, in the security measurement, the network communication is one of the most important part, but unfortunately, that part is outside of the scope of this presentation. Just briefly, I explain. Keep in mind that we consider the network communication is totally unsecure and not safe. So you should take care of your communication and data exchange. Definitely, you should use secure channels like TLS or SSL with strong algorithms. You can implement different type of security mechanisms like certificate pinning or proxy detection mechanism in order to protect your data against network-based attacks like man-in-the-middle or stuff like that. Okay, so far everything is encrypted, safe, and confidential. But the application must be secure against the local brute force attacks, because usually brute force attacks are detected by the server-side application. Developer suppose that everything is all right in the local part, and when the application side receives the OTP and username, for example, count the wrong number of attempts. And for example, after 3 times of wrong attemption, the server-side application blocks the user accounts. Or, for example, forbidden the user for a period of time, for example, half an hour or 1 hour. But there are some possibilities to brute force the PIN code locally on the device. The secret key must be fully random. Otherwise, an attacker might be able to predict or brute force in order to find the correct secret key. It should be unique. Definitely, for each user, you need to produce a unique and long enough secret key. Check before sending the secret key to the user that you haven't produced this before. And please keep in mind that it should be random bytes, not random characters or numbers. Why? Because when you encrypt something with any algorithm, might be triple DES, DES, AES, or anything else, someone else can brute force to find the secret, to find the encryption key and see the result. For any encryption key, the decryptor returns some data. It might be a garbage bytes or might be the right plain text data. The way an attacker might be able to realize if the encryption key is the right or not by analyzing the result of the decryptor. If you use random characters, not random bytes, which I faced already in one of our projects, definitely the PIN code will be 4 or maximum 8 digits. So it's not really hard to brute force that, especially when you attack some encrypted data locally. So an attacker just needs to cycle the possible PIN codes and see the result. When he sees the full characters sequence of output, that means the tried PIN code is the right PIN code. Why? Because it's almost impossible in practice to receive full characters from a wrong PIN code. So the only correct PIN code can decrypt data and returns the full characters. But when you use random bytes, it's totally impossible to recognize if the encryption is successful or not. Make sure that you use a strong type of encryption and just stores the key. don't concatenate anything to that. For example, you don't need to append the, for example, username or the current time to the secret key and then encrypt that and store on the device. Because any clue in the encrypted text can help an attacker to brute force and find the correct data. Don't use the padding scam in your encryption, because the padding bias can be a clue for the attacker in order to recognize the correct and successful decryption. Okay, now currently, what I have experienced in our test, the way developer currently using the fingerprint authentication is, in the first step, in activation, 3 first steps are the same as past. User enters the information, the server-side application returns the secret key, and next step, application asks the user if you want to enable fingerprint authentication or not. You want to use the PIN code the same as the past. In that case, if the user doesn't wish to use the fingerprint authentication, so everything will be the same as the past, the secret key will get encrypted with the PIN code and get it stored on the device. Everything will be fine. But if the user wants to use fingerprint authentication, in that case, first, the application encrypts the data with a PIN code and stores the encrypted secret key on the device. Then, application manages to access the key store through the Fingerprint API, encrypts the PIN code, store the encrypted PIN code on the device, and use the key store in order to store the encryption key for the encrypted PIN code. Next step, when the user wants to log into the system or signing a transaction, first the application asks the user PIN code or fingerprint again. For PIN code authentication, everything will be the same as past. Nothing is changed. But if the user wants to use the fingerprint authentication, first, the application uses the API of operation system in order to authenticate the user fingerprints. In case of valid authentication, the operation system gives the permission to the application in order to get access to the key store. Then the mobile app retrieves the encryption key from the key store and manages to decrypt the PIN code from the device. Now the application has the PIN code and can use that in order to decrypt secret key, and finally generates the OTP and send to the server, tag along other information, and authenticate the user or sign a transaction. Okay, still everything is confidential and everything is encrypted. So what's wrong here? What's the security issue? The issues is the software-backed key store is fully accessible to the root user. A new generation of the key store, which is hardware-backed, the root device doesn't have access to the whole key store. But currently, in the previous generation of key store technology, which is software-backed, when you route a device and get to the Android shell through the root user, you have the full access to the key store. The key store works in a way that if an application generates some data and stores that in a key store, the only authorized application or user is the generator application to access to the stored data. But root user can access to everything stored in the key store. Fortunately, this issue sorted out in hardware-backed, but currently millions of devices don't support the hardware-backed key store, and the application must be secure in even old devices. Also, Mobile banking is one of the most important application type because it deals with your money. So if there's something wrong with that and someone can access and break into that application, that means that attacker has access to your money. Of course, definitely you have faced some people who use the same PIN code for everything, exactly everything. Maybe for credit card, debit card, online banking application. If that person has different accounts, bank account, probably he or she uses the same PIN code for everything. So in the current situation, if someone can break into the phone or the device, basically, get access to the software-backed key store, and manage to decrypt the stored PIN code on the device, that means the attacker has the PIN code for everything of the target. Any other application, maybe for his credit card, his debit card, or anything else. Of course, this is the user mistake, but a good and secure application must be able to somehow cover even the client's mistakes and try to keep data confidential. If you want to use the fingerprint authentication in any other way, beside of the PIN code, the current ways needs lots of change in the database, in the server-side application, in the structure of application, or maybe communication, network communication even. Of course, you can use the fingerprint authentication and PIN code authentication both together to build more capabilities, for example, like two-factor authentications. So we should find a good, easy, and cheap way to implement this type of authentication. And fortunately, I can recommend you a really easy way to use fingerprint and PIN code authentication both together with the less change in your application. The trick is splitting the secret key in the client side to the two different size parts and use each part for a different type of authentication. Let's first take a look at OAuth algorithms, which is used for generating OTP. There are three real famous and common algorithms: HMAC-based or HOTP algorithms, TOTP or time-based, and OCRA, challenge response, which is usually used for signing transaction-based generated challenge. All of these algorithms need three important parameters, and based on these parameters, the OTP is generated. First is secret key, which we are talking about, and try to keep it confidential. The next one will be moving factor, which will change in each generating OTP. Can be the current time, usually epoch time, or the counter. The counter is a number which is get increased after generating each OTP. And finally, the coefficient, because the result of those algorithms will be a number, a float number between 0 and 1. It cannot be 0 and cannot be 1, but something in the between. So by coefficient, we will determine how many digits the OTP is. For example, if you use 1 million as a coefficient, your OTP will be 6 digits. 10 million generates an OTP with 7 digits, and etc. Now, an overview of this approach will be, I suppose the whole key is 30 bytes, will generated by the server and gets into the mobile application. When you receive this secret key on the mobile application, you just need to split that into two parts. For example, in this case, I splitted that into one 20 bytes part and a 10 bytes part. And I'm going to use the 20 bytes for the PIN code authentication, 10 bytes for fingerprint authentication, and if the user wants to use two-factor authentications, I'm going to use whole 30 bytes. If I want to categorize this, the PIN code authentication needs the key with 20 bytes. Of course, that is just an example. You can obtain your coefficients and size based on your secret key length. But in this case, I will dedicate 20 bytes to the PIN code authentication, and the generated OTP after calculation will be 7 digits. If the user authenticates with a PIN code, he can log into the system and sign transactions. But if he wants to just log in with a fingerprint authentication, 10 bytes of the key will be used in order to generate OTP. The OTP length will be 6 digits, and the authority for this type of authentication will be just login. That means a user can just log in with fingerprint, check the, for example, transaction, check the account balance, and cannot make a transaction. Just, I can say, readable permission. That's it. If the user authenticates to the system through the two-factor authentication using the PIN code and the fingerprint both together, the whole secret key, which is 30 bytes, will be used, and 8 digits OTP will be generated. Why I'm using a different lengths for OTP? Because in the server-side application, I need to recognize what type of authentication has been used in the mobile app. And based on that, I need to reproduce the OTP in order to validate and confirm if the user can log into the system and it's the correct OTP or not. Let's dig into this approach. Again, from the beginning, when the user wants to activate his or her account, first insert the information, then get respond with the server by a secret key. But the 3 remaining steps, the mobile application will split the received secret key in 2 parts. First part will be 20 bytes, and the second part will be 10 bytes. The 20 bytes will get encrypted by a PIN code and will be stored on the device, the same as the past, normally. But the 10 bytes, the remaining 10 bytes, will get encrypted by a random encryption key, gets stored on the device, and the encryption key will be stored on the key store and will be accessible in the future by the fingerprint authentication. So, so far we have activated our mobile application, and now we want to use that. So, when the user wants to log into the system, if he decides to use fingerprint authentication, which allows him to just check the back account, and he cannot, for example, make a transaction, the application tries to authenticate the user by his fingerprint. In case of successful authentication, the operation system allows the application to access to the key store. So, the application retrieves the smaller chunk of the secret key, which is encrypted on the device, and retrieves the encryption key from the key store, manages to decrypt the smaller part of secret key, and generate OTP, and proceed with the login process the same as past normally. But if the user wants to use PIN code in order to authenticate, maybe he needs to, for example, sign a transaction, the application asks the user to input the PIN code. Then the application tries to decrypt the PIN code, decrypt the longer part of secret key, which is encrypted and on the device. Then by the plain text of secret key, which is the larger part and is 20 bytes in our case, managed to generate OTP and send that to the server-side authentication and proceed with the other process. The third type of authentication we can have is the two-factor authentication. In this case, the application asks the user first to input the PIN code. Then application decrypts the larger parts of the secret key by the PIN code. After that, the application asks the user to authenticate himself via the fingerprint. In case of successful authentication, now the application can decrypt the smaller part of the secret key. Finally, application joins again two parts of the secret key and manage to generate OTP by the whole key and sends that to the application, the server-side application. Now, everything is done in the mobile part, in the client side. We need to go to the server-side application. Now, in the server part, we received some authentication request, for example, a username, an OTP. But first step that I mentioned is the activation process. In the activation process, you have a storage database and generating the secret key. As I explained at the beginning, we won't have anything to do in this part because the secret key will be generated the same as the past. You don't need to store something new. You don't need to change your database. But when you receive your OTP, the server-side application now receives the OTP. First, the server-side application needs to check the length of the received OTP. Why? Because it needs to determine which type of authentication is being used. So, based on the length of the OTP, first, the server-side application, this normally and the same as the past, retrieves the secret key from the database for the user. And based on the type of authentication, it might use the whole secret key, or the same as the client side, might chunks it to the different part. And just once, for example, use the 10 bytes for the fingerprint authentication, use the first 20 bytes for the PIN code authentication, or the whole secret key for a two-factor authentication. After deciding about which type of authentication is being used and determining the correct length of secret key, application, the server-side application, can reproduce the current OTP and see if the OTP is the correct one or not. After that, can give the user permission to the login to enter to the application or rejects that. That's based on the validity of the OTP. So we don't need to change too much stuffs in your application, especially in your server-side application when you have usually heavy storage, heavy structured databases, and maybe parallel or load balanced servers. You just need to add a switch case, maybe a structure to your server-side application and in your mobile application with the less change. But maybe someone has an old device, and the device doesn't support the fingerprint authentication. Definitely, your application must be able to be ran on any Android device. So, first, the application should check if the running device has the sensor, fingerprint sensor or not. If it does, so it can manage to use both PIN code and fingerprint authentication. But if the current device doesn't support the fingerprint authentication, you can use the only two-factor mode. How? Just behave with that like a traditional way. You can just imagine there is no fingerprint authentication and user can just input the PIN code. So hold the secret key as the encrypted text and use the PIN code. Instead of splitting that, just use the PIN code. It stores whole secret key, encrypt whole secret key, and stores that on the server, on the storage. And everything, all the steps, activation or logging or signing the transaction will be the same as the past. Just imagine there is no fingerprint authentication. That's it. Now, we need to know if this way can sort out all security issues. As I explained it at the beginning, There are two most important security issues with the current using of the fingerprint authentication. First, if someone can break into the system, into the device of a client, he might be able to retrieve the PIN code, the clear text of the PIN code. So the attacker has the PIN code, which might be the same for different applications, different accounts, different maybe cards, credit cards, or other stuffs. And if you encrypt the whole secret key and puts in the device through just a fingerprint authentication and someone gets access to that, that means an attacker can get full access to the bank account. He can log into the system, he can make a transaction, he can sign the transaction, and basically he will have full permission to the bank account. But with this way, if even someone breaks into the device and manages to somehow breaks into the key store in any way, finally he will achieve the smaller part of the secret key. And whatever he can to do with that, just maybe log into the server, log into the application, and see your bank account balance, or I don't know, see your reports, see your transactions, but he cannot, for example, transfer money. Of course, some of your confidential information will be revealed finally if someone gets access to this part. At least you can save your money. That's a good point. And your PIN code doesn't reveal. Other parts, other applications will be safe. And definitely, an application or a developer cannot cover fully and 100% user mistakes. If someone, for example, steals a client's mobile phone and manages to break into that, or for example, if the user shares his or her own PIN code with someone else, it's not something to be covered by the developer or by the application security. So part is based on the users. They must obey some security rules and try to keep, for example, their device confidential, PIN code confidential, and manage to keep it safe. But in case of any problem, this approach can save your confidential data better than the current implementation of the fingerprint. And this way is really the easiest way to be implemented with the less change, in the code and the database. Okay. Is there any question, maybe? Yes.
Hey, thank you for the presentation. It was very good. But what I want to ask is, so to the approach that you described right now, just by authenticating with the fingerprint, you would not be able to sign transactions. You would be able to log into the application, and this would make it safer for software-backed key store. But in the case of the hardware-backed key store, would we really need it, or is it secure enough to just have the fingerprint authentication, and it would be very difficult to get hacked? What do you think?
Definitely the hardware-backed key store. According to what Android says, it's fully secure and it's inaccessible if, for example, with even the root device. But you don't know the version of the device of your clients. You develop an application and it must be runnable in any type of device. Maybe hardware-backed, maybe software-backed, maybe new version of Android, maybe old version of Android. So the application must be able to take care of its security itself, not by relying on the operation system. So we are talking about the secure application, not based on the operation system.
Yeah, for that it makes sense. I just wanted to know about the hardware-backed, if you were targeting just for applications that have hardware-backed key stores, just for Android devices. So it's safe enough?
Yes, it's safe enough.
Okay.
Definitely.
Thank you.
No problem.
I have a I have a question about libraries of encryption that obfuscate data. Like they say that they are very secure and impossible to crack, but I don't know if it's that really possible. I think it's not. What do you think about it?
Basically, all type of encryptions, for example, if I understood your question right, for example, AES, DES, or triple DES, for this case, you can just use the block ciphers. You cannot use stream ciphers because the key cannot be fully random. User must be able to determine a pin code, limited pin code. So if you're thinking about being breakable, it's really hard to brute force the whole key. But the fact that is when the pin code is being used, pin code is concatenated with some other data. For example, maybe the device ID, maybe some random bytes, because it's not fit to the block size. The smallest block size is 16 bits, 16 bytes. So it's really hard to brute force 16 bytes. But user determines, for example, 4 digits as a pin, and the application concatenates that with some random bytes, for example, or makes a hash from that, use, for example, MD5, SHA-1, stuff like that, in order to generate enough lying bytes to be used as a key. So it's possible to brute force and crack into the algorithms, encryption algorithms, but when the secret key is fully random bytes, you cannot recognize if you have decrypted the cipher text successfully or not, because the result will be random bytes. It's not something detectable. But if it's a sequence of characters, you see that you got, sequence of characters.
Okay, but maybe I explain myself wrong, but those libraries, you store something there. You don't need to give them any key to. So I mean, they usually don't have to put a pin or something. So that's what I don't know if they are really encrypting it or just obfuscating.
Basically, obfuscation isn't encryption. Obfuscation is just a way to make it unclear. And obfuscating is usually used for source of application. How can I say? If you obfuscate someone, it's usually hard to deobfuscate that and retrieve the original shape. So obfuscation cannot be used for secret key because you need the exact secret key. You can't just encrypt that with a key or decrypt that. If you mean there is a way that doesn't need PIN code or fingerprint authentication, I'm not really sure because secret key must be encrypted in a safe application, of course. And obfuscation isn't if application has an algorithm in order to obfuscate and deobfuscate the secret key clearly, definitely by reverse engineering, because you know the Android application can be reversed really easy and you see the source code. So an attacker can easily read the source code, finds the algorithm and see how the obfuscation and deobfuscation are working, and without any secret key, without anything, retrieves the plain text of the secret key. So it's not, can say it's the worst way to store the secret key without an encryption.
Okay, so I have, I think, a simple question. You know that on the...
It doesn't work, please, a bit louder.
okay, so you know that on devices you can have multiple fingerprints. Do you think that there is a security issue when the fingerprints change into the device? And if yes, what can be done in order to avoid some security issues?
Okay. Basically, as far as I know, the API of Fingerprint gives you the ability to check if something has changed in the stored scan of fingers or not. When you want to use that, it alerts you that new fingerprint has added it to the device. Do you want to trust it or not? And that's the way you can just add some amount of authorized fingerprints and use that. For example, I have a phone, and I managed to use fingerprint authentication for my mobile application. If you somehow manage to add your own fingerprint, when the mobile bank application wants to use fingerprint authentication, the API alerts that and says, these fingerprints has already added it. Do you trust it or not? And usually, as far as I know, for security reasons, mobile banking applications avoid to accept new fingerprints. That's the way to protect against that.